Hi, I'm Carly Moss and welcome to my video on deformation in structural geology. Deformation is anything that has happened to a rock since the rock was deposited. And strain is the total result of all things that have happened to the rock. So for example, these sedimentary layers were once horizontal, but now they're very folded. So strain is what happened in between. We'll be focusing on pure shear and simple shear today. So the matrix of pure shear is seen here. This 0 is always a 0. Kx and ky is how much the rock is elongated or compressed, and this 0 is internal rotation. So you see here that the rock was compressed one way, which caused the elongation in a different direction. That's indicative of pure shear. The other type of shear, simple shear, is different because of this gamma term. Gamma is the tangent of phi, which represents there is internal rotation in simple shear. So this is the phi, which is from the original, which is represented by the box, to the current representation, which is represented by this rhombus. And gamma is seen here, which is just the distance from the original to the new point. This kx and ky, again, is the elongation, and the 0 is, again, always 0. Kn represents how long the rock was compressed or elongated. N is representative of the x, y, or z direction, and the equation is the current length divided by the original length. The current length of this outcrop is just this whole length, while the original is the whole quartz vein. So this shows that this was shortened. We're now going to do a simple problem using ooids, which are the spherical grains of limestone that together create an oolitic limestone. They're always spherical and have, in this case, a radius of 1. We're going to understand what happens if an ooid went under an internal rotation of 45 degrees, switched twice as long in the x direction, but preserved volume. What would be the shape of the new ooid? Here's our example ooid, the sphere right here. And we're going to try to find the deformation matrices. So we're going to use the deformation C's, kx, ky, 0, and gamma. To find gamma, we know that it underwent an internal rotation of 45 degrees, which is phi. Tan of 45 is 1. So in our matrices, that's 1. To find kx, it was stretched twice as long in the x direction than original. So this is the current length is 2 divided by the original, which is 1. So it's 2, so this is 2 here. So to find ky, we know that the volume was preserved. So kx times ky is 1. So ky equals 1/2. To find the points, to find the new ooid, we're going to draw a square around the old ooid, just to make things simpler, and use these corner points and multiply them by the deformation matrices. So this is 0, 0, 2, 0, 2, 2, 0, 2. We're going to multiply it by our deformation matrices. And you can do the rest. After completing all the deformation matrices times the original point, we see that our new ooid looks something like this. And the axes that were once like this have switched to look like that. Rocks are in 3D, so we usually use a 3D matrix to understand deformation. Kx, ky, and kz are elongation in the x, y, and z directions. Gamma xy, gamma xz, and gamma yz are internal rotation, and zeros are, again, always zeros, which makes it a triangle matrix.